Hello, this is Paul from Foresight Tech. In this lecture, we are going to find the derivative functions that we defined it from the last topic, right? Here is the definition, and the derivative function is a function. We given any x, we mapping to the y value, which is the derivative, right? Okay. And before we're going to do the calculation, I have to mention other notations. In the history, we have a lot of notations. This is the very famous one which they are using right now. And like this, so f prime of x, right? This is the most common notation. Another is a y prime, and the dy dx, df dx, because of y is f, right? Dx d dx at f, and this is just as similar as this. We put f separated to d and the dx. That I will show you. D dx is a operator. We call it differentiation operator. Differentiation, which means the procedure to find the derivative. Okay. And this d is differentiation operator. This dx is the same. Can we see we have a lot of, right? And here we have a dimension dy dx. We call the Leibniz notation. Who is Leibniz? In the history, there was a great debate between Isaac Newton and Leibniz about who founded the calculus. That's interesting, right? And finally, we have these results after the debate, and we gave a contribution. We gave credit to both Isaac Newton and Leibniz, and we say both of them develop calculus separately and independently. Okay, really, to both of them, I made a great contribution to calculus. So dy dx. Why we wrote the dy dx? Okay, Leibniz use this. Why is dy dx? Because you know the limit, the derivative is dy dx, right? dy over dx. This is the average rate of change. Take limits. You know this is the derivative. Okay, so delta y, delta x, so Leibniz changed to dy dx. So that's the reason. And we like this so far with their use. Okay, and we have another. If we want to specify the derivative at a specific point x equals a, how do you say this? And if we use this prime notation and this Leibniz notation, we say dy dx, put a bar, okay, beside, and then the subscript we put x equals a, which means the derivative at x equals a, which means f prime at a, f prime of a, right? And this is the notation. And now we're going to do one question. Okay, and we based on the definition, we to find to calculate the derivative functions. Okay, you can see. And here the question. We have a function here, and we're going to find the derivative of the function, which means the derivative function, right? Okay, and the derivative functions, we have to use the definition. Let me show you the definition is this. Okay, we have f prime, right? Okay. We have f prime of t. This is the derivative function, which means the derivative at a specific t, right? But t is a variable, of course. And the definition is this. Let me write down. Is the limit h approaches 0, and then the average rate of change delta y. Delta y is f t plus h, right, minus f t. This is delta y, and the delta x, the difference between x is h. See that the definition. This is the most common definition, right? Okay, we use the definition. Now, what do we need to do? Okay, and then we need to find the results by simplification. Okay, need to simplify everything, find the limit, which is the derivative function. Now all I need to do is do this. Let me directly plug f into this formula, which means the limit h approaches 0. Now we have this fraction. Okay, f t plus h is replace t by t plus h, replace t by t plus h. So what do we have? 2.5 times t plus h squared plus 6 times t plus h. Okay, and this the one, and the minus fx is that. Let me write it down. 2.5 t squared plus 6t. Okay, this is the delta y. On the top, the bottom is h. Okay, and then we need to do what? We need to expand this power and then to compound like term to simplify. All we need to do is do that. Let me simplify that. Okay, so I'll put it here. And so you can see that's the original. Now we're going to do what? Let me get another paper so we can rewrite. So I was going to simplify to the top, which is 2.5 parentheses, and it is perfect square t square plus 2th plus h square, right? And then plus 6t plus h, and then minus 2.5t square minus 6t. Okay, and then I distribute, which means I have a 2.5t square plus 5th plus 2.5h square plus 6 distribute 6t plus 6h minus 2.5t square minus 6t. We are going to simplify. Can you see? And this term are the same. We cancel. H square we left. How about the h? 1h. Let me see. It's only on this, right? Okay, so I have one more term. This term and this term are the same. We cancel. I think that's all we can do. Let me see how many we get. 5th, right, left. 6 I get this first, plus 6h, and then plus 2.5h square. Okay, this is the numerator. Let me write down this to there. Okay, so what do we get now? We get this. We get h approaches 0. The denominator is h, and the numerator is this one. Okay, so I copy this to there. So we have 5th plus 6h plus 2.5h square. Okay, it's almost. So now what do we need to do? And then we go to here is by simplify, right? By simplification. And then now what do we need to do? And the h and the h we factored out. So do the normal way. We can do this. We can factor out the h on the top. Okay, after factor out the h, see what do we have? Okay, the bottom is h, the top is h, then 5t plus 6 plus 2.5 times h, right? And then now what we can do? So h common factor, we can divide it out h, and almost have the results, right? H equals 0. What do we left? 5t plus 6 plus 2.5h. Okay, and then this is polynomial, and t, don't worry. Okay, so the variable now in the limit is h. So this is a linear function of h. Is a polynomial, and then we can directly substitute. So per log h is 0 to here. we don't have this, so what do we have? We have 5t plus 6 final. So we have 5t plus 6. See, this is a function of t, which is the derivative function. That's all. Thank you.